So for these energy exchange processes that involve the transfer of heat or work, we have to take into consideration the sign conventions that accompany these transfers. If heat is absorbed by the system, Q is positive. That means that heat is coming into the system. So heat coming into the system, that means that the system is absorbing heat from the surroundings. That means an endothermic process. Q is positive. On the other hand, if we have heat leaving the system, like an exothermic process, such as the reaction of heat generating reactants, we would end up having a situation where we have an exothermic process, and therefore heat would be negative. Now, for work, when work is done on the system by the surroundings, such as in the compression of a gas, that means that a height is lowered or the imaginary weight is being pushed down. That means that work is done on the system by the surroundings, and therefore work is positive. On the other hand, if we have a situation where the system is pushing out against this imaginary weight in a frictionless piston, then work is being done on the surroundings by the system, and therefore work in that case is negative. So this is a quick illustration that of a example problem that shows us how we take these sign conventions into account as we're working problems. The problem says if an electrical motor produced 15 kilojoules of energy each second as mechanical work and lost 2 kilojoules as heat to the surroundings, then what is the change in internal energy for the motor each second? So we're told that the motor produced 15 kilojoules as work So now the question becomes, what is the sign on this 15 kilojoules? Well, if the motor produced the energy, then that means energy is being lost to the surroundings from the system. The system is producing the work, and therefore the sign for work is negative. Then we lost 2 kilojoules as heat. So if we're losing heat, that means that the system is heating the surroundings because heat is being lost from the system and transferred to the surroundings. Then the sign for heat is also negative. So we're trying to find the change in internal energy for this system. So therefore, delta U is equal to Q plus W. And we have Q is equal to negative 2 kilojoules plus W, which is equal to negative 15 kilojoules. So our value of the change in internal energy for this system would be negative 17 kilojoules. That's about as simple of a problem as you could ever ask for. So now, here is another one, and this is for you to practice on. So we know that the measurement of internal energy consists of a work component and a heat component. So we're going to look at each one of those components separately. First, we're going to look at how we can measure or calculate work for a system. There are many types of work that can be done on or by a system. The most common one that we're going to use is expansion work, where we have the external pressure of a system and expansion process such as a gas expanding being pushed against that external pressure under a changing volume. And we call that kind of work PV work, or pressure volume work, or expansion work. And this is the basic equation for expansion work, and we'll show you in a little bit how that equation is derived. There are many other types of work that we can consider. One of the other common types of work is electrical work, and we'll see how we can use that in a little bit. So, actually not in this particular unit, but down the line in the next semester of the course. So, this one is the one that we're going to focus on, this expansion work. And we're going to show you four different ways, the basic equation for expansion work and 3 different scenarios that you can calculate work in an expansion for. Okay, expansion work, it's called expansion work, but it also applies to when a gas is being compressed as well. First, as I just told you a few seconds ago, we're going to show you how the general expression for work is derived. We're going to show you how to calculate work for a free expansion process. I think that's going to be the last thing we do. Oh, that's going to be the first thing we do. Then we're going to show you how to calculate work when we have a gas or some that is expanding against a constant external pressure. And then we're going to show you how work is calculated for a reversible expansion. Okay, let's start with the basic definition of work, or the basic equation for work. We know that work is equal to the force times distance, or force times height. So force times a change in height. Force times a change in height. And since we're talking about force against motion against an opposing force, the work will be against an opposing force. So therefore the work will have a negative sign. So when we're talking about a change in work, that's what these D's represent. Small change in work. dW is equal to negative force times change in height. Then that's our basic equation. But there are some things that we can relate to this. We know that if we're talking about an expansion process where we will be talking about a constant external pressure, then we can relate this work to pressure. We know that the definition of pressure is force divided by area. And so therefore, we can solve for force as being pressure divided by area. Okay, so now if we plug this value in for force, we end up having that the change in work, dW, is equal to negative pressure times area times a change in height. So, if we look at this graphically, let's say we've got ourselves a couple of different states here, going from one state to the other. Let's say we've got this container that has this frictionless piston that we love to talk about so much. And this piston has an area of A. And let's say this is state 1. And let's say, as we talk about an expansion, which is what we would have in term when we're talking about expansion work, in an expansion, the height of that piston would be raised from state 1 to state 2 by height, h. So if the piston has an area of A and is raised to height h, area times height, or should I say change in height here, would be equivalent to a change in volume. So area times a change in height is the same thing as a change in volume. So therefore, we can say that dW is equivalent to negative pressure times change in volume. So the pressure that we're talking about here is this external pressure that is opposing the system, not the pressure inside the system. So the pressure that we're talking about is the external pressure times the change in volume. So now if we wanted to integrate over both sides, we would end up with W, work. We will take the external pressure outside the integral because we know it is constant pressure, and differentiating over dV, our solution would simply be V, and we know if we go from the final to the initial state, did I just say that? From the initial to the final state, after we solve for that integral, the answer is V. And now knowing that we have to say initial to final, we subtract the final state minus the initial state. We end up with our overall basic definition for work, which is that work is equal to the negative external pressure. I'm sorry about the stylus, it's a little thick here. Let's see if I can try that again. So is equal to negative of the external pressure times the change in volume, which is the same thing as saying V final minus V initial. So that's our basic general expression for calculating expansion work.